You are at a depth of 27,349 feet, or about 8,336 meters. The pressure around you right now is 830 times the pressure you felt this morning when you woke up. The water temperature is nearly 36 degrees Fahrenheit, which is close to 2 degrees Celsius. It will not change from here on down. No light exists at this depth, not because your equipment is broken, but because sunlight has never reached here since this ocean formed. At this pressure, proteins in the cells of living organisms begin to deform. Cell membranes can no longer maintain their structure. Enzymatic reactions stop working. This is not a theory. This is physics, measured, confirmed, and documented in scientific literature decades ago. And right below your camera, something is swimming, not drifting, not falling, swimming, fast, and it is eating. This is what the record shows. Pseudoliparis bellaevi, also known as the Haddle snailfish, is a transparent, scaleless, pale pink bony fish that is about 12 inches long, which is approximately 30 centimeters. It is smaller than your forearm. It has no hard jaws. There is no bone structure thick enough for the pressure to crush. From the outside, it looks like something unfinished, like a first draft of a fish, not ready to exist in any real environment. On August 26, 2022, a camera was dropped into the Izu Ogasawara Trench off the coast of Japan. At 27,349 feet, which is about 8,336 meters, deeper than any bony fish ever recorded in the entire history of scientific observation, it appeared in the frame. Not a carcass, not a specimen pulled up from a net, a living animal, moving freely in an environment where every existing biological model determined that vertebrates could not exist. This is not a story about a deep-sea fish. This is a story about a cell. It is about how chemistry works here, and why the answer requires rewriting what science has long considered settled. But that is only the first problem. This is what the record shows. The physics of pressure on living organisms is well known and specifically measured. At around 400 atmospheres or more, proteins begin to misfold, not because of temperature, but because physical pressure squeezes the molecules together in a way that alters their spatial shape. When proteins lose their shape, they lose their function. Enzymes no longer recognize their substrates. Cell membranes, which need to remain fluid to transport molecules back and forth, become rigid. The cell does not die from a lack of oxygen. The cell dies because it is no longer a cell. This is why for decades, marine biologists set a theoretical limit of around 19,685 to 22,966 feet, which is about 6,000 to 7,000 meters for vertebrate species. Not because of a lack of food, not because of a lack of oxygen, but because the basic chemistry of a living cell, protein structure, cell membrane fluidity, enzymatic catalysis, is designed for a certain pressure range. Crossing that threshold is not a problem that evolution can solve by building a harder or thicker body. That is a limit of chemistry, and chemistry does not negotiate. But before the snailfish, there were signs. Amphipod specimens, small crustaceans, were recovered alive from below 26,247 feet, which is equivalent to 8,000 meters. Their tissue analysis revealed something unusual. The concentration of a small organic molecule, trimethylamine N-oxide, also known as TMAO, was unusually high, and it was not randomly high. It was high according to a systematic pattern. The concentration increased steadily with depth. Specimens from deeper water contained more TMAO, consistently and predictably across every species tested. No one knew why, until they looked at what TMAO actually does to proteins under extreme pressure. TMAO is a pizzolite, a pressure-countering molecule. Under high-pressure conditions, it wedges itself between proteins and prevents them from misfolding, not by strengthening the protein structure, but by changing the chemical environment around the protein to the point where pressure no longer impacts it the same way. Evolution did not build a pressure-resistant organism. Evolution rewrote the chemistry inside the cell so that pressure is no longer an issue. And this is where the data begins to get unusual. Timao is not a new discovery. It has long been recognized in common marine fish, which is why ocean fish have a characteristic smell when exposed to the air. But the concentration of Timao in Hadal species is on a completely different level, and when researchers began to systematically measure Timao from 656 feet down to 26,247 feet, which translates to about 200 meters down to 8,000 meters, they found a pattern that no one predicted. The concentration increased linearly with depth, not randomly, not by individual species. Linearly, as if there were a formula that evolution found and applied uniformly across all lineages living here. At 6,562 feet, or about 2,000 meters, Timao accounts for about 40 millimoles per every 2.2 pounds of tissue, which is about 40 millimoles per kilogram of tissue for the species living there. At 16,404 feet, which is about 5,000 meters, 70 millimoles. At 26,247 feet, or about 8,000 meters, more than 100 millimoles. This concentration is so high that if you were to hold a snailfish that had just been brought to the surface, which is impractical because they disintegrate when pressure drops suddenly, the smell of Timao would be overwhelmingly strong. This is not just an interesting detail about fish odor. This is evidence of an organism operating a chemical system completely different from any vertebrate ever studied on land. But that is only the first problem. If Timao increases linearly with depth, and it works, then theoretically, an organism with enough Timao could exist at any depth. No limits, no ceiling, but Timao is not an infinite solution. At a high enough concentration, Timao itself begins to harm the cell. It interferes with proteins in other ways, disrupts osmotic balance, and causes cellular stress through its own mechanisms. There is a tipping point, a biochemical limit after which the antidote becomes poison. And when researchers extrapolate the linear line of Timao concentration to that tipping point, the number that emerges is around 27,559 to 27,887 feet, which is about 8,400 to 8,500 meters. The current record for the snailfish, 27,349 feet, or about 8,336 meters. The theoretical ceiling for Timao, 27,559 to 27,887 feet, which is about 8,400 to 8,500 meters. The distance between the deepest recorded vertebrate and the point where chemistry completely collapses is less than 656 feet, or about 200 meters. Not an accident, not a coincidence. This is an organism operating at the absolute limit of what chemistry allows vertebrates to survive, and it is hunting there, actively, purposefully, right at the border beyond which no vertebrate can exist in any form. The 2022 expedition did not just record a depth record. They observed behavior. The snailfish is not just trying to survive down here. It is dominating this environment. It is the most clearly documented predator in this trench. In an environment that no other vertebrate can enter, Pseudoleparis has no competitors. Chemistry built it a kingdom, and it is ruling that kingdom from the very bottom of what can exist. Science does not have an answer for this. Not yet. This is what has been documented. Timao-based pressure adaptation does not just appear in the snailfish. It has been found in amphipods, in certain species of polychaete worms, and in some species of Hadal shrimp. These lineages do not share a common ancestor at Hadal depths. They come from completely different evolutionary branches. and each branch independently found the exact same molecule, the same mechanism, and the same rate of concentration increase with depth. Evolution replicated the exact same solution multiple times, from different materials at different times, in a place where no one even knew anything lived until less than 50 years ago. This is not fully explained. There are hypotheses, but there is no consensus. The tipping point of 27,559 to 27,887 feet, which is about 8,400 to 8,500 meters, is a prediction, not an observation. No one has tested it directly because it is impossible. To test it, you would need a vertebrate living there. If it can survive, the prediction was wrong. If there is nothing there, that is not proof. That is the absence of proof. We do not know where the absolute ceiling of vertebrate life is. We only have a number from an equation, and a fish approaching that line at the speed of evolution. The deeper question is not how Tamao works. That has been described quite fully in terms of mechanism. The question is, why Tamao? Out of all the organic molecules that could exist in the marine environment, Tamao is the one that multiple independent lineages converged upon. Not another molecule with a similar structure. Not another enzyme solving the same problem. This exact molecule, in every lineage, every single time. A complete answer to that question, in a full evolutionary chemistry sense, does not currently exist. We can describe what the snailfish does. We can measure the results. We cannot explain why the chemistry of the universe has a loophole that allows this to exist, and why evolution found that loophole multiple times from different starting points in a place where light has never reached. As of the most recent recorded expedition, unknown. This might be showing us something else entirely. For a long time, the question of life elsewhere in the universe was framed in a single way. Look for Earth-like conditions, liquid water at surface temperature, sunlight, equivalent atmospheric pressure. The snailfish existing at 27,349 feet, which is about 8,336 meters, is not in spite of chemistry, but because it rewrote chemistry. This is not simply a structural adaptation. This is proof that the right conditions for life is a concept far more flexible than what science assumed. Europa, Jupiter's moon, has an ocean beneath an ice sheet that is 6.2 to 18.6 miles thick, which is about 10 to 30 kilometers. The pressure at the bottom of that ocean is estimated to be equivalent to what the snailfish is enduring right now. Enceladus, Saturn's moon, has hydrothermal activity beneath its ice layer, confirmed by data from the Cassini spacecraft. If Time, or a molecule with a similar function, can evolve independently multiple times on Earth to solve the pressure problem, there is no reason to rule out the possibility of similar chemistry occurring elsewhere in the solar system. The snailfish does not prove there is life on Europa. It proves that we cannot use the chemistry of Earth's surface as a benchmark for what can exist. And there is another thread, one that is being actively researched right now. Tamao and related piezolites are being studied in the field of tissue and organ preservation for transplantation. When cells are frozen for preservation, the pressure from ice crystals causes cellular damage through a mechanism similar to ultra-high pressure. The molecules that the snailfish uses to keep proteins functional at 830 atmospheres are being tested to keep human cells functional during cold storage for organ transplants. The bottom of the ocean is teaching transplant medicine, a transparent, scaleless fish, smaller than your forearm, living at the very edge of what chemistry allows, in absolute darkness where no other vertebrate can go. It does not know that. It is just eating. But inside every single one of its cells is a solution that evolution has found multiple times, in multiple places, from multiple different starting points, for a problem that we still do not fully understand. There is one more thing the record shows. During the 2022 expedition, the camera did not just capture a single individual. It captured a group, multiple fish, moving, competing for food, and interacting with each other. At 27,349 feet, or about 8,336 meters, there are enough snailfish to form an observable social dynamic, enough to form a functioning population. This is not a stray organism at the limit of possibility. This is a species thriving there. Documenting what exists down there takes years to accumulate, if you want to follow what is recorded before it becomes widely known. The archive is open. The depths still have plenty to show you.